hopefully some of you. So to be a bit provocative, Alberto was saying I'm going to talk about probabilistic aspects and how we use the weather in the short term. I'm not going to talk so much about probabilistic stuff, and I'm also going to get rid of the weather forecast eventually as input, so that we focus on some of the recent problems. And I thought if I lighten the framework, then it's easier to discuss these challenges. I have to say thank you to two collaborators. There's Jakob Messner. Jakob Messner is a meteorologist from Austria who came to work with me, and Yongning is a mathematician from China who also worked with me for a little while. We got funding from EDF for this work, and I'll explain you why. You'll see the data sets after, and we got some other fundings also from Denmark. All right, on. Okay, doesn't work, the remote. We'll do without the remote. Okay, yeah, we'll do it like that. So what I'm going to discuss is the motivation for going for these high-dimensional problems, and then I'll go through some technical proposals. I'll skip the mathematics. Do you want to see a lot of mathematics or not? Maybe not. No, you're not sure. So we'll see. I'll look at your faces when they're mathematics. Maybe I'll skip. But some of the key aspects is that the first 2 points would be about high dimensionality, and I'll explain you why we care about it. And the last point would be about distributed learning, and also, again, I will explain you why we care about distributed learning and what it is in practice. Okay. Sorry. The PDF is a bit funny. All right, so I'm going to talk about wind, because when you come from Denmark, you care more about wind energy than solar energy, even though it's not really true today. We have a lot of solar energy in Denmark. I've seen also on the way from Cambridge to Norwich, you have quite a lot of these solar farms. Even though it's not very sunny, it's still profitable enough. But when you come from Denmark, wind is an obsession. You know, we care a lot about wind. And if you think of wind power forecasting, the traditional approach is that we consider there's this wind farm I care about, or this few wind farm I care about, and I'm just going to design a model or some kind of approach to forecast there. So you would have some gridded weather forecast, and so you would always have 4 points around your wind farm of interest. You're going to downscale that to the level of the turbines, be at the right vertical level for the hub height. So you're going to have your dedicated weather forecast if you want. And then based on that, you're going to model the conversion from the turbines from weather energy, you could say, to the actual electrical energy. So that would be the classical way. I mean, this has been proposed 20, 25 years ago. But still today, a lot of people who are in the business of providing forecasts, that's what they do. They really focus on predicting wind farm by wind farm. The problem is that, do you know how many wind farms we have around there these days, or how many solar power plants? It's getting huge, so we cannot afford to do it at each and every location. And then also it seems a bit dumb to do it for each and every location individually. There we can learn a lot from weather and climate science, where you look directly globally at all the points you care about in time and in space. All right, so some of the first works, we're focusing on the fact that maybe if we start having a lot of wind turbines around, instead of looking at wind turbines as the point of focus, what they want to predict for, we can also look at them as sensors, because these wind turbines are recording a lot of information, and this information can be used to improve forecasts. And obviously, if you look at Denmark, this is Western Denmark. The weather fronts are most likely coming from the west, southwest. So you could see this wind farm on the west side of Denmark as sensors, and then you can use the information measured at this location, let it propagate, and then you could improve forecast on the other side of Denmark. So obviously this is not a seasonal timescale. Yes, so this is the west and this is the east. This is not about seasonal timescale because we talk about hours. I mean, the improvements you may get are for 2 to 5 hours lead times. But still, this general idea of using the data from the wind farm as sensors is something that we should do in general, whatever the time scales and spatial scales of interest. So when this has been done, for instance, for Denmark, these numbers that you see here, they are the improvements in terms of root mean square error. Root mean square error is the classic lead criterion that's used for evaluating wind power forecast. And so these are improvements in root mean square error you can get just by post-processing your forecast using information from the other wind farms. So you can see on the west side, for instance, there's not much improvement because actually the wind farms are used as sensors. but then the wind farms on the other side, they profit of the information from the west, and you can have quite high improvements up to nearly 20%, all right? So these were some of the first proof of concept. I mean, this is from 10 years ago, this kind of ideas, but this has motivated people to look for these spatiotemporal dependencies. Alberto was telling me, you know, we have similar experiment for solar power in Germany, same ideas in Australia, etc. It's a pretty straightforward idea. All right. But then I was telling you we have many wind farms today, and also I think we can safely say this is a global phenomenon to have more and more solar parks and wind farms. So we should look at ways to scale it up to the continental level. We've built this data set with some colleagues that called Europe, and it's available on Zenodo for any purpose, commercial, research, whatever. And our point with designing this data set is that we should actually look at the whole European level, because we are in it together with this renewable energy deployment and how we're going to operate the system. So we might as well directly work at the whole European level. The system here is simplified. This is a simplified view of the power system on the top left. This is extremely simplified. Actually, here there's around 1,000 nodes. If you look at the true power system in Europe, this would be more tens of thousands of nodes, right? So it's quite simplified. But still, in terms of the signals of interest, so wind, solar, and electric consumption, we've used the ECMWF data, and we've simulated what would be the forecast and the actual observations for wind farms that are spread all over and solar parks that are spread all over. So this data set can be used as a basis for doing some forecasting studies. This is obviously more for short to medium term. The forecast we got from ECMWF, they are for up to 10 days, something like that. So yeah, but the point is that we should look at the whole European level at once. Right, and eventually this would be this ground forecasting challenge. I would really like that we're able, the same way meteorologists and climate scientists have done it, you know, you don't really look at a single location. You have models that are global, or at least for a big area. And so we should do the same if we want to predict renewable energy or any kind of variables for energy applications. This should be consistently done for the whole European area, because if we don't look at all the space-time dependencies and the dependencies between the sun, the wind, and temperature, precipitation, etc., actually we're going to miss out on a lot of important features. So hopefully this will happen in the future, and we need a lot of people in it together, so that can be meteorologists, mathematicians, power system engineers, etc. Oh yeah, no, it's because there was an embedded video, but you don't have it. Hopla. All right. So now there's something that is quite interesting that I skipped here. If you try to predict for tens of thousands of locations at once, you build one single model, you can bring the biggest supercomputer that you have. You're not going to be able to actually run a model for predicting for all these wind farms and all these solar parks at once. If you think of ECMWF and some of the other weather centers, they have some of the most powerful computers in the world, and still it takes hours and hours, you know, to issue the weather forecast. This would be pretty much the same for wind farms and solar parks. If you really want to have a single model to predict for all the location at once, you would need huge supercomputers, and still it would be fairly slow. So some of the challenges we have is that we want to sparsify the problem. Do you know what this means, sparsifying in mathematical terms? So that means that if you look at the dependencies in time and in space, a lot of these dependencies should be actually zero, right? So if you think of winds, if you have a location in the north of Denmark and in the south of Spain, it's really unlikely that wind is going to be correlated, right? So we can say already we don't care about the connection between these 2 points. And there are lots of reasoning you can do like that, so that you say actually the relationships I need to learn, there are very few. We don't need to learn dependencies for all location in time and in space. And that's sparsity. We try really to find the minimum set of dependencies and learn them or use them in our model. So this is a paper we wrote. I mean, we wrote it quite some time ago. I don't know why it only appeared. I think they had a long backlog. It took 2 years for this paper to be eventually an issue. It was written quite some years ago. And that's why it can get a bit mathematical. But first, assume that you have a model where you get measurements for each and every location. So let's say you have, I don't know, 100 locations, and at a time t, you get a measurement for wind power generation, and then you get a vector with 100 values like that, right? At time t plus 1, maybe it's 10 minutes after, you get also a vector of measurements. And in statistics, they have this idea, what they call a vector autoregressive process, or VAR, that we can write a linear model for connecting the observation at a certain time t with the observation at time t minus 1, t minus 2, etc. If you do that, you can actually have all the space-time dependencies that are going to be accounted in your model, and it's the simplest way to do it because it's easy and linear, right? The coefficients you would have in this kind of models, they would be matrices like that, matrices of coefficients. And this idea of sparsity I explained. In practice, that would be that if you have this kind of matrices that are trying to link the measurements at different type points and different spatial locations, most of the coefficients in this matrix should be 0. And 0 is white here, right? So the non-zero coefficients are in red. So this is for lag 1, and this would be for lag 2, for instance, if you consider dependencies for 2 points in time. And you see, when you learn a model, you would have non-zero coefficient on the diagonal. So somehow what you observe at time t is dependent on what you observed at time t minus 1 at the same location, and at time t minus 2 also at the same location. And then the off-diagonal elements are for what you observe at other locations, right? So if you focus on predicting at a certain location, maybe you care about the information at some other location the time before, right? So there's some transport of information from one location to the next. You see, most of the coefficients here are zeros, and also in this matrix, which is hidden by a thing. But okay, you see the point. Actually, 90% or 95% of the coefficients will be 0. So you want to impose that. There are different ways to do it. You can do it in a fully data-driven manner. If you go see people from statistical learning or machine learning, they will tell you it's easy to do. And you can also do it using some expertise. So what I told you earlier, we all know that wind in the south of Spain and the north of Denmark are not going to be related. So we could bring this expertise in the model. And we talked quite a lot with people from EDF, looking at the climatology of wind and also looking at solar climatology in France. You know that there are some dependencies that just should not exist. So Brittany, for instance, and Côte d'Azur, there's not much dependency in terms of wind, all right? So we can bring that in. And the way we're going to do it is that if you write a model, I told you there's this model with some matrix of coefficients, we're going to impose that a lot of these coefficients are going to be zeros, but we're going to do it almost by hand, you know. We're going to have a mask. So if you do a bit of meteorological modeling, you know, you have this land sea mask, right? So that you're going to make some limitation, what is land, what is sea. Here, somehow we do the same. We put a mask, and we decide which coefficient should be non-zero and which should be 0. And we do that based on some expertise, all right? And then we only try to learn the coefficients that are expected to be non-zeros. So that's the idea that's put there. That's where it gets a bit mathematical and technical. You don't need to think too much about that. The thing is that if you do statistical learning, what we want to do to learn the model coefficients, we want to minimize some kind of least square criterion. So you may think of it as the RMSE for your forecast error. And we want to find the coefficients in our model that will permit to minimize the RMSE. That's what this objective function means. And then what I was explaining to you just now is how we build a mask. And what's important is here more on the right. What we say is that we want in our matrix to have a maximum number of non-zero coefficients. So somehow you know that you don't want to have more than 10% of your coefficients that are going to be non-zeros. You know that for each and every wind farm, there cannot be more than, I don't know, 5 other wind farms that can be used to explain what's happening at the wind farm you care about. You know that you don't want to care about more than a certain number of past observation, etc., etc. All right? So we can do these kind of things, and our colleagues from industry were quite keen because you can bring a lot of expertise from operators in there. The problem is that as an optimization problem, this is very nasty because it's non-linear. So we had to reformulate that. And there are ways to reformulate it. Yeah, so that's what I was explaining. You know? There are ways to reformulate it so that you learn from the correlations you observe in the data. So if you look at your wind fields or some solar power production fields, we can learn the correlation patterns, and based on these correlation patterns, you define the mask, okay? If you do that, we can rewrite the models in a more compact way and an easier way. So that's what we did here. And that makes that we have less parameters somehow to set. And then it's also easier in terms of optimization. Eventually, we get to a problem where everything is linear. And if you do some optimization, you always prefer to play with linear models. All right. So let's apply this kind of idea. So we had 2 case studies. We have a lot of data from Denmark, obviously, because we have wind farms spread all over the country. On this side of Denmark, I have a data set with nearly 400 sites. 400, they are not wind farms. We have a tradition that we spread the turbines a bit everywhere. So a wind farm is actually more a connection point of all these turbines to the power grid. And so we have 400 of those. Here, for the example, we only took 25 that we randomly choose. And we have data at 15-minute resolution. So that's not really seasonal, but it's just to make the point. And we have a lot of data in time. We have years and years of data, so that permits to make a lot of nice studies. We've been comparing quite a few models. There's the classical benchmark model. So persistence is what you see is what you get. You know, you use your last measurement as your forecast for any time in the future. You can use some autoregressive models. So that's the idea I explained to you. You use some information from the past to predict what's happening in the future. But with this one, you only use local information, not the information at the other wind farm. Then the spatial temporal models are trying to use the information from all the other wind farms. And the models I just presented the previous 2 slides are these 2 models. These other 2 we'll discuss later. All right, and these are the performance metrics that people classically use. RMSE, mean absolute error, which is pretty much the same idea as RMSE, except that it's absolute value of the errors that you care about. And then we'll look at the sparsity, so how much there is in terms of information in the coefficient matrices, so how many non-zero coefficients we have. And what the metric might be the opposite, but that's the idea. All right, so these are some comparison, and we look just at 1 step ahead forecasting, that's 15 minutes ahead. These are box plots for the RMSE improvements that we have, and you have here some values for the average RMSE for the different benchmarks. So that's persistence, the autoregressive model, the vector autoregressive model. So if you don't try to impose a mask or try to learn the sparsity, and then the 2 models I was presenting. All right. In terms of improvement, the improvements are very small in using the spatial temporal information here because it is very short lead times. So there's not so much information. If you do it for further lead time, there will be more improvement. And then you see that actually the various type of approach that you can use for accounting for the spatial temporal information yields pretty much the same kind of improvement. You see it's around the 5% improvement on average. The thing is that these models are quite cheap to run, while this model is very expensive to run, right? So we can get a lot of benefits in a very, very cheap manner with this kind of idea. And also we bring the expertise from the operators. If you go talk to this power company, they love the fact that as a forecaster, you account for their opinion, and their opinion enter the model eventually. Okay, there are questions from the webinar?
Would you like to take them now or at the end?
I don't know. Are the difference in RMSE? Yeah, there are. That's why I was saying there are lots of data points because the data sets.
Maybe repeat the question.
Oh yeah, there's a question by Laurent Dubu asking if the differences in RMSE and mean absolute error are significant. And I was saying yes. I mean the data is so much that any kind of hypothesis testing will show you that the differences are significant. And you can assume that for any result I show, because we use so much data, the results are always significant. All right. Yeah, if you have any question, you can stop me whenever you want. It does it again. Okay. So the thing is that as much as it's interesting to put a mask on the data and bring the expertise from the operators, you saw the model. It looks very heavy and it looks very technical. So with my other collaborator, Jakob, the first part was with Yongming, my Chinese collaborator. The second part was with Jakob. So with Jakob, we thought, can we not do it in a way that is fully data-driven, and we don't have to worry somehow about defining this mask and do all this kind of optimization. And in machine learning, there's this idea that's called lasso. So lasso is about how you're going to learn a large set of coefficients, but you're going to penalize the coefficients so that all those that you feel should be zero, you just force them to be zero. And it's done automatically as you learn from the data. The problem with lasso is that it's not made for this big model, this big vector model, vector-based models, and also it's not online. And by online, I mean that for us, we want that at any time point when we get new data, we just want to learn on the fly. We don't want to always use a big batch of data from the past, learn from that, and then you slide by one time point, and again, you have to learn from a big batch of data, right? So if you do it online, you have the advantage of using recursivity. You just update your coefficients on the fly. So there's also a paper available online. You can use it. All right, so let's start from the definition of this vector autoregressive model I explained you earlier. So this Y here is a vector of measurements, power measurements at a wind farm, wind farms, for instance. So let's say 100 wind farms. And we say that what we observe at a certain time is linearly dependent to what we observed at previous times for all this wind farm. So the coefficients A are matrices, all right? So if you have 100 wind farm, the dimension of this matrix A is 100 times 100. So it gets very big rapidly, these matrices of coefficients. And it's the easiest way you could ever model this kind of relationships. If you want to fit a model, I was telling you we use this least square approach. We want to minimize our MSE so that afterwards, somehow we're going to use the information we collected recently, we multiply it by these coefficients, and that will allow to make a forecast for the future. We want this. Look, I told you we want this to be sparse, and the idea of lasso is that we're going to penalize the coefficient matrices. So this is the matrix norm for the coefficient matrices, and we're going to penalize it to try to force to have as many coefficients as possible equal to 0. And then this lambda is going to make a trade-off between the least square fitting you want to do and the penalization of coefficients. We also want to adapt to new information because wind or solar, if you look at the signal from the power measurement, it's non-stationary. The characteristics change with time. I mean, you can imagine looking at wind time series in winter, in summer, in spring, the dynamics in wind are quite different. If you look at offshore data, we actually also have wind dynamics that change from one day to the next, depending on the local situation in the coastal area. So you need this kind of adaptivity. We do that by down-weighting the data in time. So you give quite a lot of importance to recent data when you learn, and you down-weight the importance of the older data. And this is done with this kind of exponential forgetting. All right? This is where I'm not going to go into detail. We've wrote some way, some algorithms so that you can update the coefficient very easily. So you can do the stuff I showed you before in a very cheap manner, and you can update your coefficients in real time and always track so that you learn the latest dynamics in your wind power measurement or in your solar power measurements. Right, it's very fast. Okay, some examples. If you think just of a first order process, first order vector autoregressive process, the matrix of coefficients, so we have only one, we call it A, right? So we have here, I think it's 10, it's a 10 by 10 matrix. And I was telling you, we use some sparse matrix of coefficients. We have coefficients on a diagonal, and we have quite a few coefficients off diagonal. Those that are numbers, we impose them. And these guys, we're going to make them vary. Where are they? Yeah, you have A1, A2, A3, A4. We're going to make them vary, and we're going to want to track them. So see how we can learn them in time. All right? So these are the true coefficients, A1, A2, A3, and A4, and how they vary in time. We have a data set with 15,000 time steps. We only show you the last 5,000 here. We have some coefficients that vary very smoothly. Some coefficients that are jumping around. You may see it as some kind of regime switching behavior. So for wind, think for instance of some weather system that is passing over an offshore wind farm. So you may have convective cells, for instance, and then you have high wind variability, and it's on and off if it's there or not. You may have some coefficients that fluctuate all over the place, and you may have some kind of flat coefficients. You know, it's the dependency always is the same. All right. So if you were to estimate that batch, so you just estimate once for all, you don't try to account for time adaptivity, you would get these blue lines that you have in the different graph. And obviously, I mean, for the coefficient that is just flat in time, it works. But for these coefficients that vary in time, somehow what you estimate is the average value of the coefficient over time. And if you use this concept with the tracking of the coefficient value, you may be able to track the smoothly varying coefficient, not the crazy varying coefficient, maybe not also the regime switching coefficient, but at least those that are smoothly varying or that are flat, obviously, you will track. Eventually, we also managed to have something sparse, so more than half of the coefficients are seen as zeros. It's not as good as it should be, but still overall, you manage to impose these conditions. All right, so here's an application. We consider 100 wind farms in Denmark. I say we have nearly 400. It's the same kind of resolution. We transform a bit the data so that it's nicer to play with, but you don't have to worry about that. And you see this wind farm are spread all over Denmark. So this is like 250, 300 kilometers distance. And here it's like 120, 130 kilometers. All right. So this would be the coefficient matrices that we estimate. All the points that are blue, red are non-zeros, and all the white are zero coefficient. So you can see that's a lot of coefficients that are zeros in these matrices. We really managed to keep it sparse. And the very interesting thing with this method is that we manage with 200 wind farms. I think the example we had for France after it's 200 wind farms, we can do it extremely fast. Well, if you use the classical methods, it would be extremely slow. So that's a very big difference. And also in terms of RMSE improvement, these are the RMSE improvements that we get with the different methods and different lead times. So lead times are here on top, 15 minutes, 30 minutes, 45, and 60 minutes. And then the methods that we compare are here. So the autoregressive method is when you only use the local information. Then you have the vector autoregressive model. So you use space-time information, but you don't try to be online and sparse. And this is the method that I just showed you, where we try to be online and sparse. So you can see here the improvements are almost double for the short lead times, and quite significant, but not double for the longer lead times. And as I told you, if you go from this method to this method, this one is much cheaper in terms of computation. All right. So this is proposed for wind, but this can be used for solar. This can be used also for financial time series if you want to do some trading. I mean, there are lots of potential applications for this kind of modeling. All right, I was telling you we had also a French data set. It was a work with EDF actually originally, and there is an R package that has been released. So there's an open source package that you can use to try it out, not with the French data because the data is confidential. But yeah, the results for France were pretty similar, all right? So these are the forecast improvements that we got with the different methods. And you can see with this online sparse learning method, you can get double the improvements of the not online, non-sparse method, and it's much cheaper. All right, there's one last point I want to discuss. It's distributed learning. Everything I told you before, we had all these wind farms, for instance, in France, all right? I say I'm going to improve forecast by using the information from all the wind farms, right? They're all sensors. But you can imagine that there are different people owning these wind farms, right? Okay. So what's the likelihood you think that these people want to share data? Very low. Extremely low. Extremely low. It's our experience. I think I've been in this business for 15, 17 years. If there's one thing I'm sure about, people don't want to share data, right? So any of the nice thing we're showing you here, and when I go to conferences and everything, is based on the assumption that people are going to share data, and they are not, okay? So that's actually the true problem that we want to look at. And how we're going to do that, we have to design some approaches to do distributed learning. So if people don't want to share data, what we can do is that we can design some kind of market, if you want, where I own a wind farm, I want to improve forecast for my wind farm, and I'm going to pay you to help me for that, all right? So that's why I say we have a central agent, so consider it's me with my wind farm. There are some contracted agents, so that can be people who have wind farms in the area, and I'm going to pay these people so that they help me to improve my forecast, okay? So they could do that by sharing data, but they don't want to. So instead, we're going to flip the game and we'll say, okay, I'm going to design a forecasting model, and I'm going to split it in bits and pieces. You're going to do some calculation for me based on your own data. You're going to send me back the result of your computation. So I don't see your data, you did it locally at your wind farm. But when I merge all the information, I'm going to get a better forecast, all right? So that's an idea that is not 100% new, but still for renewable energy, it's not been done before that. Oh yeah, I wrote a paper in 2016 that described the basic idea, and I think there are a few more papers that have appeared since then. All right, so can we do that? Yes?
Quick question, what do operators get for sharing the data? If they were to share data?
So the data themselves. I say first they don't want to. What would they get? What they could get paid, hopefully. That's another question. Can we design data markets so that people would feel an incentive? Most often what happens today is that if people would share data, it's more because they are obliged. So it's not, no one has actually thought what should we give them so that they share data. It's more like we're talking in the US, they've said, okay, you have to. In Europe, we've said, you don't have to. And the point of this work is more to trigger the discussion, as you say, what could we set up so that people feel they would like to collaborate or they would like to share data. Another idea, we're going to have a summer school at DTU in June, and the keynote speaker on the first day is from MIT, and he's been working on data markets. How can we design data markets so that people share data and get paid for it automatically, right? So that's one way. Here, the idea is to say more, no, I don't want to share data and be paid for it. It's more, I'm going to pay people so that they do bits of computation for me, and when I merge the information, I get better forecasts, right? And so they are called contracted agents because obviously I'm going to have to pay them to say thank you, all right? There's no blockchain involved, before you ask. Yes?
Can I just check here whether you're talking exclusively here about wind speed data or power output data?
No, so that can be any data, by the way. We've been looking at some ideas for new projects, and some of the ideas where it would be most relevant is actually, you see they're liberalizing the meteorological sector, and some people in Germany, for instance, private companies could have met stations. So think of sky imagers. You have a sky imager, I don't know, somewhere 5 kilometers away, right? And I have a solar power plant 3 kilometers away here. Maybe I would like to use your sky imager data to improve my solar forecast. So it could be any data. For wind, it's weather radar data, for instance. If I could see some convective system coming, I would be very happy because that would improve my forecast. So it doesn't have to be consistent also the type of data or any kind of data that could help me improve. I could have a contracted agent, does some work for me, I get the data back. Yeah.
Why do people choose not to share data?
Oh, that's, how long do we have? No, I mean, there are many reasons. One, it's a market-based world out there, so people feel that they have an advantage by keeping their own data and their own knowledge. And traditionally, plus in the energy sector, especially in wind, it's been incentivized because all your data is actually linking you directly to the kind of deal you get from a banker or an investor. So you would like to keep that private. If you leak any data, people can know somehow what your wind farm can do, what kind of rate or deal you got with the banker or the investors, and you could use that maybe. I think most of these reasons are actually rubbish. In practice, if people wanted to share data and were retributed for it, they would realize it's not such a big deal. That's why in my conclusion, you will see my idea is that now we should go for these data markets. And we already wrote some papers for Denmark showing that if people share data, everybody would win. It's like a cooperative game, you know, everybody would win really if we were sharing data. But we don't want to. That's yeah, another story. So there are different 5 minutes. There are different setups where we could consider there's an interest in doing these kind of things. We've been thinking of a single wind farm operator. You could think a single solar power plant operator. And you may think people in your area you want to contract to help you. A portfolio manager, so you may, for instance, trade for 3 wind farms together. They are in red, in the plot. And then to improve your forecast for these 3 wind farms together, you could contract some of the other guys in the neighborhood. Or you could be a system operator. Today, the system operators collect the data from everybody. But with this kind of idea, you could say, well, I don't want to collect the data, just keep your data, do the computation for me, and just give me your pieces of information that I'm going to merge. So for the system operator, it's not such a big deal because they can impose to have the data today. But for these 2 other setup, it is a big deal to do it. All right. So to do that, that's where I'm sorry, it's a bit mathematical again. We're not going to go into detail. The basic idea I want to show is that we still can write some easy linear models. It doesn't have to be, but that's the simplest setup we can consider. So you can say that to explain what's happening at a certain time, you have, I don't know, a constant that can be a bias. And then you have some local information you have access to, and you have a linear models for that. And then you have the non-local information, so you don't have access to, and you also want to make a linear combination of that. So you could write this model at once if people were sharing data with you, and you would be able to fit your model, use it for forecasting, etc. We will also use this lasso estimation so that we minimize the number of non-zero coefficients. And here it actually has an advantage because eventually you want also to minimize the number of people you want to contract. And all the people for which the coefficients are 0, that means their information is not useful for you, so you don't want to pay them anyway, right? Okay. So if I was to do it centralized, I would do it like that. But if you look at the literature on distributed optimization, when we write models like that, we can split it in bits and pieces because everything is linear, it can be decomposed, it's very easy. And there's a method called ADMM that's been made very popular by a professor in Stanford, Stephen Boyd. And we're not going to go through the algorithm, but there's an algorithm so that you can split. So that's the vector of coefficients, beta. You can split into beta 1, beta 2, etc. with, let's say, beta 1 is me, my local coefficient with my data. Beta 2 is the coefficients of someone in the room with his or her own information, etc., etc. So now I'm going to split this vector of coefficients, and everybody is going to estimate their own coefficient just based on their own data, all right? So that's what we do with the algorithm. I ask each and every agent involved here to estimate their own coefficient based on their own data, all right? And then I have a process for merging that eventually, right? I never see your data. I'm just going to merge some information for coefficients that you inform me about, all right? Okay? So eventually, when we use this kind of idea, we can apply it in forecasting mode in the same way. You can say, can you make partial forecast for me just based on your local information? And then using this kind of idea, I can merge that and make a forecast overall, where I can make a better forecast than if I only use my own information, okay? Good. So that's a bit technical, the algorithm, but actually it's you implement that in R or Python, it's 12 lines. It's not very difficult. All right. So we've done that for datasets in Australia and also for France. And so the dataset is confidential for France, so you cannot have access to it, sorry. But the data for Australia is public, so you can download the data, reproduce, etc. if you want. And we're just going to do one step ahead forecasting. Since then, we've extended that to day ahead forecasting or week ahead forecasting, where you try to share or not information. Okay, so yeah, 2 minutes left. All right, so we've been comparing adding a model, so persistence, this benchmark, what you see is what you get. And it's very short-term forecasting, so it should be very competitive. Here it has an RMSE of 360. If you use an autoregressive model, so you use your local information, you could get a little improvement. And if you were to use the offsite information, so this distributed learning idea I just proposed, I could improve a bit more again, and I've never really seen the information of the others, all right? So the numbers look a bit little, but it's just 5 minutes ahead, and it's actually one of the most difficult data sets I've played with. All right, what is interesting here is that since we've used this lasso idea, I only needed 1 or 2 contracted agents to improve my forecast. So I have 22 wind farms here, and actually for each and every wind farm, if they want to improve their forecast, they only need to contract 1 or 2 other wind farms to help, okay? And that's very interesting. You don't want to have to pay everybody to help you, otherwise the value of improving the forecast completely vanishes, right? Okay, we've done that for different setups, so for different wind farm, different periods, etc. And the kind of improvements we get were on average 5%, but it could go down to 0, like nothing, and also up to 10%. You can do that for portfolios, and so portfolios, since you have a bit of smoothing effect, there's more signal and less noise, it's a bit easier to learn, all right? So the improvements we got were more in the order of 15%, right? And 15% improvement in RMSE starts to be quite a lot. And here again, when considering this portfolio effect, we only needed to contract 1 or 2 wind farms to get this kind of improvement. So that's quite interesting in terms of setup. So this was 8 randomly chosen wind farms in the French data set. And we considered a lot of these potential wind farms. Here we have a case with the aggregation of all the data. So that's the system operator case. And you have a very little improvement in doing the distributed learning over just using your own data as a system operator. Here, it's not such a business case anyway. Here, the most important thing is that you change the game. Like, people never share data with the system operator, and you still get very good forecast. So people might actually be happy. You get the same forecast accuracy, but I never have to share my data with the system operator. If you go to France, for instance, and we have some French people online here, they would tell you people are a bit obsessed with sharing or not sharing data. So maybe it's good if you can get the same forecast accuracy with people never having to share data. All right, so a few concluding thoughts. First of all, if you were ever to do some forecasting for renewable energy, you have to accept the fact that it's going to be super high dimensional and heavy. My personal experience is that 5 years ago, the most important thing in my life was to convince my head of department to buy me a supercomputer because we're dealing with such big data sets, and it was so costly that not having a supercomputer would be the end of my research. So just accept the fact it's going to be high dimensional. And then this idea of distributed learning might be some of the most exciting game changer if we could get benefits from let's say doing like data sharing but not actually sharing the data. This could be very good. Eventually, what we want to do, and this we've already done, is that we want to do it online. So I was telling you earlier, we want to lighten computational costs and also adapt to new information. So to do it online is the way to go. And we are finishing a paper on that should be submitted soon. Then you want to also to broaden it to more general models. Here I only showed you with simple linear models. It's possible to use sky images, a lot of different type of information, but it's really involved, the type of modeling. So it's something that needs to be done. Then some work we've already done and people are getting quite crazy about it is that you can also add a crypto layer, because actually what I showed you here, the fact I say, I'm not going to share data, I'm distributing computation and you will never know what I have, but I can write some other optimization problem where I can double guess actually what's your data from what you gave me to help me to improve my forecast, all right? And if everything is linear like we did here, I can actually find out what data you had in the first place. So what I showed you actually can be broken. So what you need to do is that you need to add a crypto layer, and this is not very difficult. It's very mathematical, but it's not super difficult. So this is some of the work that we're doing. And then eventually what we need to do is, I mean, we had the super interesting question earlier. We have to think of the business case. I mean, what would you pay people for they share the data or they help you with computation? Or, I mean, what does it take somehow to change the game? And then on the other side, we have to see what are the benefits. Because if we have, as a trader, for instance, I'm going to make, let's say, 100 euro more per day because I improved my forecast, but I had to pay you 95 anyway, was that a good idea in the first place? All right. So there's a lot of interesting questions, but yeah, that's what makes research exciting. So thank you.
Okay, thank you very much, Pierre. And as you have noticed for the audience on the online, we have an audience here as well. So it's a double seminar and webinar. That's why we were clapping as well. And we haven't heard your clapping though at home on the office. But you can ask questions if you want online, and we take a few questions also from the audience here, please. Do we have questions? Yes, please, Steve. Yeah.
It seemed to me that you always selected a subset of wind farms from those available. For example, I think you chose 100 out of 350. Was that from the point of view of testing your methods on unseen data, or for some other reason?
No, I mean, here it's just for the sake of example, because it gets very heavy when you want to show results for everything. For some of the methods I showed you, we actually already applied to the full EU dataset. So we have, I forgot, 1,300 location. But then when you want to discuss data for 1,300 location, it gets completely crazy. So for the sake of example, it's better to use these smaller test cases. It's more for that.
And it wasn't on data quality or?
No. They are randomly chosen anyway, so there's no no points of data quality or anything. No.
Okay, other questions from the room? I have
bored with my.
So I have one question. Yeah, and
Is that a first one?
yeah, you can ask one, please.
To what extent do you think is it more important to ask operators to basically calculate different things and give you data, or is it more important to convince the government to tell operators to give you data?
Yeah, so the question is about, yeah, what should be the setup eventually? Should we force people to share data?
It's like American policies versus European policies.
My take on that is, I think people don't really realize what's happening. In maybe 25 years, it's going to be fully renewable, the electric power generation. And then everything comes from the weather. So it's like a common good, right? So I think the data related to that should be also shared, because somehow we are all sharing the weather. Sure, we have wind turbines that extract energy from it, but we do it for the social good, you know, to have all this renewable energy generation. So it's a bit stupid after to let people hide information that prevent us from getting the full of this social good. So my opinion is that it would be better that authorities just say, guys, stop it, share data. You get some compensation for that in some way or the other. You know, in Germany, they've been very good at discussing it regularly, saying, okay, maybe we need to just change the game and tell people, shut up, it's just going to be like that, right? And I think for data, it could be the way to go. Because there's no, we had this question, in practice, if you think of it, there's no real reason why you would hide your data. In the long run, it doesn't make any sense. Some of the first wind farms that were installed in Denmark, for instance, we've been through that. We got their data for projects, and they were crazy. You don't share this data, you never use it in publication. And after a few years, they were telling us, oh, you can publish the data, we just don't care. They realized it was not a big deal. So I think, yeah, we should go to them.
Okay, yeah, Steve, another question, please.
Your benchmark seemed to be always persistence.
Yeah, because, yes, the question is.
I was wondering whether you ever chose to compare against a short-range weather forecast as a comparison.
Yeah, so here, so it's about benchmark. Is this relevant to use persistence as a benchmark and not a weather forecast-based benchmark? So my answer to that, here you see all the examples are for 15 minutes to an hour ahead, and then it doesn't make so much sense to use the weather forecast. I say it's also for the sake of example. I was provocative, but the real application we do are for day ahead or several days ahead. Then there's weather forecast always. So then, yeah, it's the most relevant benchmark to have the whole package, right? But here, when it's 15 minutes ahead, persistence is actually difficult to beat. Yeah.
Yeah, I think I had a kind of related question, because it's what you do is all statistical, yeah, and like when you try to relate one point, geographical point, Denmark with Spain, you can easily find the statistics, but then to go beyond and to have a better view over the next day or so on, you need to have really embed the weather forecast.
Yeah, sure.
So how did you think how to embed
so
weather forecast within your system?
Okay, it's okay. So in this kind of approach, you can do it. The models we have, instead of being based just on the data that you have locally, you use also the weather forecast as input. And then some people do some also additional statistical layer of regime switching, for instance. So you want to be flow-based, you want to account for different weather types. So these models can be extended to have all that. Again, it was just for the sake of example. Here the models already look maybe a bit complicated if you don't know the notation. But if you bring the weather information, then it becomes huge, like really huge.
Okay, so that takes us to the end of this seminar and webinar. And I just want to remind the people in the room here and the audience online, we have much more discussion happening in June. We're lucky to partner with DTU, where Pierre is from. And we'll have a conference, international conference, energy meteorology near Copenhagen in June, at the end of June. And you can also follow what Secli Firm does online here. We have a website, and this project is led by UEA, actually. So we got a team based here. There is Steve in the room, there's Claire, Louise at the bottom, and the project manager, Leslie, here in front. So if you'd like to know more about the project, visit the website, come to ask us, and online, send us emails as well. So I'd like to conclude the webinar again. Thank you very much, Pierre, for the very interesting talk, and thank you, the audience, for interesting participation. Thanks.